Hello, welcome to the last video of module 1. So here let's start by taking volume by cross section. In the previous video we saw how we can integrate the area between curves, but that was for a 2D figure. Now we need the volume by cross section, so we are finding the volume of a 3D figure. So consider like any random geometric shape, which I'm calling an object. An object having a volume can be divided into multiple small divisions of area dA. So if this object I'm taking, I can take one thin slice of this, call it dA. Now if we integrate this area, so we integrate it from the start over here A to the end B, it will cover every possible dA strip, meaning that we are getting the volume of the shape. That's basically volume by cross section. Now here we have integrating solids of revolution. A solid of revolution is formed when we take a solid and rotate it about its axis of rotation. So if this is a solid, like this is a parabolic shaped solid, and if we take the axis as the axis of rotation, when we rotate it, we are basically taking it over here, we are forming it 90 degrees, then 180, 270 and then 360. So eventually it will form a 3D figure with a circle as at any point. So the cross section can be taken as a circle. Now there are two types of methods. You have the disk method and the washer method. The disk method basically means that your axis of rotation, once the object is rotated, passes through the object. So over here, if I rotate this object down here and up here, this is the shape which will be formed, and the axis of rotation is passing through the object. The washer method, you have the axis of rotation passing in the center of the object, but the object is not touching it. So over here you can see there's a small gap over here. When I rotate it around, there will be an outer circle and an inner circle. There's an outer and an inner radius. Over here there's only one radius. The radius is measured from the axis of rotation, and over here you can see the axis of rotation is not intersecting the object. Let's start off by the disk method. In the disk method, we integrate the area of the disk given by the wall, which gives the volume of the plane. So as I said, you take every small thin strip area dA, integrate it over the correct limits, you will get the volume of the image or the figure. So we are saying that A of x, the area of any one plane. So the area of, as we can see over here, this area will be given by pi into the radius squared, but this is the radius at this point. So the radius at every point will vary, and so we are saying radius of x, it will be a function of x. So volume will be integration of the area over the correct limits, but the area is given by this, hence we say the volume is integration pi r of x squared dx if it is about an x-axis or it's a line parallel to the x-axis. For the y-axis, we will be taking pi radius of y squared. So here we have an example. But to find the region between y equals root x over 0 less than equal to x less than equal to 4, and x-axis is revolved about x-axis to generate a solid. So this region is revolved about the x-axis between these limits to generate a solid. What is the volume? We look at the diagram we have over here, 0, 0, 4, 2 as your 2 points. Now this image, once you rotate it around the axis of rotation, which is the x-axis, you'll get some figures or solid somewhat like this. So at this particular point, I can see my radius, at some point x, my radius will be a function of x. As given y is root x. Since it's directly given, we can say the radius of x equals y equals root of x. And since this is about the x-axis as well. So the volume will be integration from a to b, pi radius of x squared dx. You can put radius of x from here, we get pi root x squared dx, pi x integration from 0 to 4 because your limits are given 0 to 4. So pi integration from 0 to 4 x dx gives you the answer 8 pi units. Then over here we have find the volume of solid generated by revolving region between y is root x and lines y is 1 and x is 4 about line y is 1. So over here you have two regions, y is root x and x is 4, but you have to find it about the line. Your axis of rotation is the line, y is 1. So over here we have a slight change where we say this is your axis of rotation. Since it's parallel to the x-axis, you take a function of x. Your radius is a function of x, and it starts from here, it ends over here. Since your limits are now from over here, if you take your y is 1, it starts from here, you get x is 1 also, that's why. So to find the radius, we use y equals root of x, as we know, but the axis of rotation is y equals 1. So to find the correct function of the radius, we take root x equals 1. Your radius of x is given by root x minus 1 equals 0, which is radius at any point. So then over here we can substitute it in the formula, radius of x squared dx, and then you get your, simplifying, you get your answer 7 pi by 6 units, square units, or sorry, cubic units since it's volume. Find the volume of solid generated by revolving region between y-axis and the curve x equals 2 by y, where this is valid from 1 less than equal to y less than equal to 4 about the y-axis. So now over here we are taking the region of the y-axis. This is your diagram which will be formed, and from here we can say, okay, so x is given over here. Now you need a radius as a function of y, because you're taking the y-axis or a line parallel to y-axis as your axis of rotation. So then you can, again, rather than taking a function of x, you are taking a function of y, and that's it. The procedure remains the same. Lastly, you have the Washoe method. Over here you got two radii existing. We call the outer radius big R of x. As you can see over here, this line from the center till the end is big R of x. Line from the axis of rotation till the small circle is small r of x. So we calling the inner radius small r of x, the outer radius big R of x. And we say the area of the washer or the area of the object is equal to a of x, where a of x is going to be the area of the outer circle, outer region, minus the area of the inner region. Since these both are circular regions, it's pi r square. And the volume will be the integration of this. So this can also be written as, you can take pi out common, it's outer radius squared minus inner radius squared. And here's an example. Region bounded by the curve y equals minus x plus 3 and y equals x square plus 1 is revolved around x axis to generate a solid. Find the volume of the solid. So for this question you will have to make the graph, at least a rough graph, so you know what's happening. Y equals minus x plus 3. So this is a line with slope minus 1, y-intercept 3. Y equals x square plus 1 is a parabola. So this down here, this is the y is x square plus 1, this y is minus x plus 3. Now why do you need to make the graph? You need to know which is the outer radius and which is the inner radius you are considering. Find the volume of the solid. Okay. So now we need to find where the points intersect first. Then we can equate x square plus 1 equals minus x plus 3. On solving we get x is minus 2 or x is 1. So these are our limits, minus 2 to 1. Now we have, by making the graph, we find the lower and the higher curves. So obviously from the graph you can see the line is higher than the parabola in this region. So the higher curve, and hence the outer radius is given by the line, the inner radius is given by the parabola. So we volume integrate from a to b, pi, radius of x, outer radius squared minus inner radius squared. You substitute the values from here, you solve it, you get your answers 117 pi by 5 cubic units.